Has started and share, right? And then I go to screen. You are sharing your screen, but do you see my screen? Hello? Hello? Do you see it? Are you there? No.
Yes, sir, your screen is visible.
Do you see the screen?
Yes, it's visible.
Yes, sir, it is visible clearly.
You can see the full screen now, right?
Yes, sir. Yes, sir.
Okay, that's good. And then, I keep on seeing the waiting in the lobby and all that, so that I don't have to worry, right? Because it seems to be asking me to admit, but I don't do that, right? Mm. Are you there? Hello?
Yes, sir.
You're there. Okay, good.
We should wait a little. I think participants are joining now.
Sure. No, I can wait. I just
Little
want to
bit
make sure
only.
we have a connection.
Actually, here weather condition is rainy days are there.
Oh, it's rainy. Oh.
Yes, sir. So all are coming to their offices and their workplace. 19 people are there, so I think we should wait only 2 to 3 minutes.
Okay, I'm fine. Yes. So my question is whether audience would see my face along with the slide, or do they just see the slide?
Not, sir.
They just only see the slide, right?
Yes, sir.
Okay, I understand.
Morning, sir. I'm Surojit from Assam, India.
Good
Hello.
morning.
Sir.
Good morning.
Yes, sir. Sir, I have one question. Actually, my specialization is control system.
Yes.
Yes, sir. So then, sir, what are the future scope of control system in memory star? So can you please actually?
Actually, the memristor, depending on what type of a circuit you create, you can embed a memristor circuit into control system, for instance, hardware. So
yes,
when you are talking about memristor, it's mainly hardware aspect of it. So, for instance, I worked with my colleague on sound localization hardware using memristor. So if you have a robot navigating and then I try to find the source of the sound, it can tell robot whether it should turn 29 degrees to the left or 30 degrees to the right, depending on the location of sound. And then robot can navigate through such a sensing, sound, hearing. So that's
Yes.
one application of robot application we have done. And maybe you can create also some hardware for different applications, sensor, and that sort of things. So what interested you to attend this lecture?
Actually, sir, the topic that I have selected is neuromorphic application in
Yeah,
memory state. Yeah.
neuromorphic application.
Yes, sir. And also the synchronizations by
Right.
using yes, sir, by using a robust controller.
Yes. So yeah, if neuromorphic computing, yes, it's a good application. Especially today, I think you will hear some
Yes.
neuromorphic computing aspect. Although last lecture will cover more, but you will see some particular application circuits, memory star circuit with a particular applications. So that may be of somewhat interest to you. But in control, are you mainly on mathematical aspect, or are you also carrying hardware aspect? Are you building
Sir, both,
hardware
sir,
or
both,
what?
sir. Hardware
Both
plus,
are.
yes,
I
sir.
see. Yes. You will see some memristor, especially from Technical University Dresden. Those folks fabricated memristor for a lot of applications. You will see that. So such a hardware can be useful for robot also. Correlation function calculation very efficiently, very quickly, low power and that sort of thing.
Yes, that means, sir, suppose in control purpose, we just replace the registers by memristor. And
not just a resistor with memristor, but more than that. Yeah. So I think a memristor system can do a lot more than just a resistor array. The other thing is you can also have the memristor's resistance adjusted, digitally. So you can program the memristor for different resistance values. So that's reconfigurable to some extent. So you can have a reconfigurable hardware when you use memristors.
yes, sir. Yes, sir.
Mm.
Okay, sir. Thank you very much, sir.
Thank you.
Sir, you can start now, sir.
Oh, we can start now.
Yes,
Yes,
sir.
good morning. I understand it's raining in India, but hopefully you are in good spirit. So today we will get into circuit and systems based on memristors. So this first slide shows different aspects of circuits and systems. For instance, on the far right, you will see deep learning acceleration using this memristor crossbar, such as like this. You have rows, input rows, and then the columns, which collects all the currents depending on state of memristors. So if you have a V1 voltage applied, and then it will induce some current in this memristor. And then if you have also applied it to V2, additional current, etc. So you will have one column of current, and then another column of memristors. So it will generate another the current, etc. So this is essentially what is called the crossbar array. It's a rectangular structure, a matrix structure, and you have a memristors. Whether each memristor turns on and off, we will see more detailed circuit, but it's just a concept. It's called the crossbar array. This is very good in matrix calculation, computation, but in analog fashion based on Ohm's law. So that is a very handy module for acceleration of computation. So this shows a matrix I is equal to GB, the memductance, and then voltage vector, and you have a current vector coming out. And that calculation is done by analog fashion, which is very, very efficient. Although one has to be careful about variability of memory resistance and so on. But you have to tune this conductance precisely to do precise calculation. The other thing is the in-memory computing, right? Von Neumann architecture in conventional way separate logic from memory. So it has to be back and forth through the data bus, which is energy consuming, power consuming. But if you co-locate logic and the memory function into one location so that memory cell can do both the computation and storage, then you reduce this back and forth traffic a lot. So thus you can save lots of power. So in memory computing can be benefited from the use of memory register, because memory register is both memory and logic operation. Yeah, so it enables both the memory and the logic operation in same area. So that is also very appealing for memory store application. The other application is in neuromorphic computing, such as here you have neurons and then synaptic connections between neurons, and you can have many, many layers. But if you use a spike-based learning and inference, so it's a spiking neural network, can be sparse, which is also helping to lower the power consumption, energy consumption. So memory register can be used for synaptic weight. We will see that there is an analogy between a synapse in biological system and the memory register conductance, memductance. So that is a very good application. In the future, so we try to mimic the brain function, which is a biology-based, but we can have a bio-inspired algorithms and use memory register for such applications yet to come. And then earlier in the first lecture, people asked about, oh, is there a difference between RAM and the PC, this RAM, phase change memory? I said that they are all memory registers. It's true, they are all memory registers, but people tend to still, within it, distinguish RAM with the PCM. So that's yet to be discussed in this lecture. And earlier we talked about the conventional scaled CMOS. So based on Moore's law, we keep on shrinking the scaled CMOS. So maybe up to 1 nanometer technology can be still possible. And then if you stop, you can still go to a three-dimensional structure, by stacking these chips vertically, which who cares? Once they occupy only small volume, then that's okay, 3D. In memory, they can go all the way up to maybe more than 100 layers. So can you do for the logic? With the cooling technique, that may be a possibility down the road. But that's meaning that CMOS still has a long life to do. But there is a problem with the scale down CMOS. CMOS operation is based on charge operation, and as you shrink, the critical charge distinguishing logic 1, logic 0 becomes a very, very small amount, which can be susceptible to noise and disturbances, which is not very reliable. That's why we said maybe instead of electric charge, we should have a resistance as a state variable. And instead of von Neumann conventional architecture, despite multi-core applications, we need neuromorphic. So this is what we are heading for in the future. And this is another overview of memory register technology. A lot materials, device structures, and how they operate. and how they applied, for instance. So, you can have a phase change memory, conductive filament, conductive bridge memristor, that sort of things. And essentially, if it is a filamentary type of operation between top plate and bottom plate, you're building filament, columns of some conductive particles to make a conduction. If they are broken, then resistance is very high, for instance. In a phase change magnetic type of a thing, yeah, it either crystalline structure is nice crystalline structure, then resistance is low, is on. If it's amorphous, is disturbed, not crystalline structure, then resistance may be high, then it's off state. So it's a on-off state. And whereas here, is it broken or not broken, distinguish on-off state, for instance. So this paper is still, this particular special issue is still referenced a lot. Back in 2012, myself and Pinaki Mazumdar of University of Michigan, Rainer Wasser in Germany, Aachen, we co-edited the special issue in the proceedings of the IEEE to cover 5 important aspects of memristor technology: theory, device engineering, circuit engineering, digital and analog systems, and neuromorphic systems. So if you want to have a sort of a overview of this type of topics, this will be still a good issue to look into. June 2012 proceedings of the IEEE. I see that people are still visiting to read this paper and issue. Again, another view of memristor technology. I said the memristor materials is important. And then how do you build the structure is also important. How do you build the 3D integration is of a growing interest. Performance. Are you going to use it for switching machine, or are you going to use it for synaptic plasticity for artificial neural network, the connection between neurons? And then are you going to use it for digital logic or analog calculation and so on? So that's where this memristors can be applied. So today's lecture is about memristor circuit and systems for different applications. So you can divide into 2 groups. One is a discrete structure. The other one is a crossbar array, like a matrix structure of memristors. And in discrete applications, so you can have a digital, such as logic operation, digital logic gates, reconfigurable logic circuit, because a memristor you can, program its resistance state. So you can reconfigure this logic circuit. That's the beauty of this memristor, actually. And in analog, discrete analog application, you can create the chaos circuit, Schmitt trigger, variable gain amplifier, difference comparator, cellular neural networks, oscillators, etc. So that's a discrete device application to build a circuit. If it is a crossbar, you can still have a digital or analog. Especially analog is a keen interest to neuromorphic networks. Also field programmable analog array. Yeah, you can have a, like a gate array. You can program this gate array for analog functions, for instance. So that's another beautiful thing. Digital, you can have a memory, content addressable memory, non-volatile memory, or logic circuit. So those are the snapshot of a memristor circuit and their systems. Now, one of the toughest market is automotive market. Why so? It's human life is critically, as you know, important, and you don't want to have an automobile accident that threatens human life. So the automobile industry is very, very conservative when it choose a component. But seeing that memristor is used in automotive market means a lot in that regard. It should be reliable, it should be cost effective, etc. So that shows how robust this memristor is at the very, very high temperature, 150 degrees Celsius. You bake it essentially, and yet the variation seems to be very stable, right? And this shows that the solid line is a high resistance state, dotted line is a low resistance state. Even at the high temperature, after many, many cycles, there's still a distinction between low resistance state and the high resistance state. That means you can depend on it for logical operation and so on. So there is the small company called Weebit. Nano's RRAM technology offers a very cost-effective solution to this non-volatile memory need. Some specifics of the technology include, for instance, a two-mask adder. You only add two masks to fabricate memristor. Very few added steps compared to other non-volatile memory technologies when you use memristors. Lower wafer cost than competitive non-volatile memory technologies. Fab-friendly materials. No contamination risk, no special handling, etc. Use existing deposition techniques and tools. Easy to integrate into any CMOS fab. That's very important. CMOS compatibility and adding to it simply. Back end of line technology. You can finish CMOS and then after that you can embed the memristor. Stack between any two metal layers. You can build memristor between any two metal layers. No interference in that process. Easier to embed with existing analog RF circuit. Easy to scale from one process variation to another. So that is the beauty of a memristor, especially it's a general, but even in automobile market, yeah, they are doing it. Especially this Weebit Nano company is doing it. And as you can see, there are many components, right? Many sensors, especially I just recently am using the electric vehicle has so many sensors. In the front, there are 10 cameras. In the back, another 10 cameras. So on the front and the back, 20 cameras. So it gives me enough warning, especially when I back off. I can read very clearly the coming car and so on. Sensor is such that if I try to back off while something is coming, it automatically brakes, so I cannot move even the car. So it prevents the accident that way. And there are many other functions, right? Key entry, power management, touch screen controller, and mirror controller, and the pressure sensor, engine cool control, etc. etc. Many new circuit components, but they need to be very reliable. Cold temperature as well as high temperature. So this shows that robustness. So that is appealing, and that's very encouraging actually. Now this is what I am talking about. This Technical University Dresden. A few years back, I was visiting Chua Memristor Center. They have a Memristor Center at TU Dresden, and they created what is called the core resistor. That's a memristor. TIF memristors can become a crucial building block for Industry 5.0, Industrial Revolution 5.0. Yeah, it's fourth industry revolution. In Germany, they call Industry 5.0. And the next level data mining, thanks to its enormous potential for high precision data analysis, accompanied by energy savings and real-time sensor monitoring. So they are using this Chorister, this TU Dresden memristor for that application. So 3 unique opportunities of our TIF memristor technology. So that's their advertisement. Processes and stores data within the same cell. Yeah, that's a computing in memory application, right? Thus enabling completely new data processing algorithms in electronic circuits. So you don't have to move from logic to memory back to logic, that sort of things. Unparalleled speed, very high speed, robustness, and the flexibility in data-driven processes, power consumption, size, and cost as a standard CMOS solutions. So it's low power consumption, size is small, cost is low. So that's very appealing, right? Now, memory goes with logic a lot. When I was working at AT&T Bell Labs, we had a department doing memory design. We had a department doing logic design. They always fight each other. Memory says, the memory is more important than logic. What is logic? Logic is just a bunch of inverters. And whereas logic people will say the other way, we do all the complex reasoning, and the memory is just a capacitor. You store, the charge and bring back, and so on. But in reality, memory is also very complex and important, especially the cache. Cache within a chip is very important. So SRAM is used a lot because it's a high performance, but it's costly. It consumes lots of area. Then now they also try to embed DRAM into logic chips. So embedded DRAM, that is increasing. So you have a L1 cache, L2 cache, L3 cache, and then maybe another level of cache within a chip. And then capacitor can be limited, maybe up to 10 megabyte or even 100 megabyte on chip. But beyond that, you have to go off chip, right? So up to here is on chip, is a volatile for that application. And then off the chip, then it's a non-volatile. So storage class memory, solid state memory, hard disk memory, terabytes, hundreds of terabytes now. So that's the memory structure. And as you can see, SRAM is embedded into chip. And now embedded DRAM is also getting into the chip. So that's a good application for potentially memristor to get into this chip as well. So the memory technologies. Incidentally, I am borrowing some material from Professor Shimeng Yu of Georgia Tech. He has a nice book called Semiconductor Memory Devices and Circuit, published in 2022. It's a good book to find some good information. So I suggest you maybe go to library or download this the book and then use it for your research. So this is interesting. The biography here. This is the year from 71 through year 2020 here. And you can see that the upper curve is the NAND flash. In terms of three-dimensional stacking, the density, packing density is very, very high compared to SRAM, for instance. It's about the order of magnitude difference, 10x difference. So the Apple CPU, they use maybe on-chip memory, but about in terms of the how much you can pack, there's a lot of difference. So now looking into here, this integration density is like 10 to the 7, is 100 million, this billion, 10 billion, etc. Per square millimeters bit, a number of bits, integration density versus access time, speed. So this is a 0.1 nanosecond. This is about 1 nanosecond. This is 10 nanosecond, etc. So you can see that SRAM is fastest in nanosecond range in terms of latency. but in terms of packing density, it's very poor, right? You see here. DRAM is here. You can think of a three-dimensional DRAM. Storage class of the chip is high, and then NAND gate, although packing density is very high, it's very slow, right? It's a hard disk, and then flash memory and so on. So that shows the performance aspect of it. Now, if you look at the memory market, semiconductor market, memory is about quarter, 27%, right? And then 73% is other IC products. Within the memory, DRAM and the flash is half and half. Yeah, DRAM is a little bit more, 53%. Flash is about 43%. Yeah, so that's a sort of a memory market. And in terms of memristors, RRAMs in IC fabrication, the recent prototype chips, TSMC is doing RRAM. That's a very encouraging sign. It has a 22 nanometer now. That was a 2020. It should be like a 14 nanometer or even below. So it had a 28 nanometer, 40 nanometer, Intel 22 nanometer, Winbond 90 nanometer. So they published in VLSI 2020, ISCC 2018, 2019, IDM 2017. But if you look at the embedded flash on chip, it use one transistor, one memristor, 1T, 1R, 1T, 1R, 1T, 1R, 1T, 1R, 1T, 1R. Not just a memristor. They need 1T because to prevent what is called a sneak current. Yeah, you can accidentally have a current flowing in parasitic path. So in order to prevent that, they embed a MOS transistor, NMOS transistor as a switch. And depending on whether you selected that particular memristor or not, if you select, you turn it on, and then this is selected. If you don't want to select, you turn it off, then this is removed, for instance. So that's the sort of a bit cell structure. In terms of a bit cell size, F is a minimum feature size. So suppose it's a 22 nanometer technology, F will be 22 nanometer. So F square is a 22 nanometer square. And then 53 times of that one is one bit cell size using 1T, 1R. And, all this. Now, the other important thing is a ratio between R on and R off. The higher, the better. So the on-off ratio in this embedded flash is 4, 3, 5, 6. Intel used 4 to 10. I think Intel technology is PC RAM, phase change memory. And the Winbond, their case is 100 times. Write voltage 1.6 through 3.6. That's rather high, 1.4 to 2.4, 2 to 4. So you want to also lower this write voltage. And read pulse width, when you read, then you have to provide the pulse to turn to select a particular memristor. So this is like a 10 nanosecond width at 0.7 volt, or 20 nanosecond width at 0.2 volt, 9 nanosecond, 0.26 volt, etc. And write endurance, how many times can you write without hurting the device, degrading the device, 10 to the 4, 10 to the 5, 10 to the 3, etc. And then detention, for instance, Winbond 90 nanometer, that's only available at 85 degrees Celsius, is more than 100 years. That's pretty good, actually. Yeah. So getting basic, right? Getting basic, two-state case, simple case. So again, this is a crossbar array. You have one metal plate, another metal plate on top. It's a nanoscale. You sandwich some material in between. Like this can be platinum, and then titanium dioxide in between, HP memristor case. So if you measure VI characteristics, when you increase, it follows this lower curve. And then when you exceed what is called the VSET, some threshold voltage, it jumps to this portion. If you increase further, it follows here. If you decrease, it comes back. It doesn't switch back here. It comes back to this curve. You go to negative, comes to here, and then if you decrease further, it jumps to this portion. And then if you decrease further, it follows this one. When you increase, then follow this one, and repeat itself. So this simple illustration shows two states. Voltage versus current. Low current means high resistance. So this is a R off. The blue one is R off, high resistance. When current is higher, it's a lower resistance, R on. Logic is 1. This is logic 0, for instance. So that's the configuration. And this is what is experimentally measured and simulated for that particular case. So it behaves nicely, but in most cases, this wouldn't be straight line. It is curved. So it's non-linear, and likewise, this is curved. So that's why Leon says if you find the two states, then infinitely many states, because it's non-linear, and then depending on where you are, your resistance will be different. This is a measurement of a memristor with a sinusoidal input signal. And you can see that you have a voltage curve, sinusoidal, and then corresponding current. And as we said earlier, there's a zero crossing. Whenever voltage is 0, current is 0, etc. And this is a Lissajous figure, voltage and current figure at some frequency. When you increase the frequency, it becomes almost a linear, straight line, or a non-linear line at a very, very high frequency. This is a simulation result and the experimental curve. So the red one is a simulation based on model, and the blue one is experimental curve. It's pretty close, depending on how good your model is. This shows the frequency response. So the Lissajous figure, as you can see, 5 hertz, 10 hertz, 15 hertz. So as you increase the frequency, the red one is very thin. Hysteresis with a very, small the area in the lobe, right? So that's that. And then this is sort of the monitoring of resistance. So this is a low resistance in red, R on. It's a logic 1 case. And this is a high resistance. So in this case, it's pretty good ratio. This is about 100 here, more than 100. This is about 100K here. So 100 and 100K, so almost 1,000 difference here in this particular case. And that shows also the crossbar array, where you have many, many memristors in this case. This is each line is a 50 nanometer. So each memristor crossbar is a 50 nanometer by 50 nanometer. And when you measure this voltage IV characteristic is like this. Red one in the positive direction and blue one is a negative direction. And this is the single device, 100 micrometer diameter disc device, has a similar characteristics like this. And so again, this is the crossbar array. In this case, it's 1 micron meter wide. So it's not nanometer scale, but for this, they did a measurement. And then this is a positive lobe, and then negative lobe flipped. So this really should be like this coming, but for display purpose, they flipped and then like this. So as you can see, if you follow this one, section 1, and comes down, and follow this section 2, and then turn around section 3, and then continue section 4. So 1, 2, 3, 4. So you will have a different memristors, state 1, state 2, state 3, state 4, for instance. So in this particular case, you can establish 4 different states in this memristor case. Instead of a binary, you will have a 4 different state. This yet shows a different device structure. So you can see that you have a red one pair, which is a low resistance state that allows a high current, and then a high resistance that allows a low current. So you have this one pair, and then another green pair for different excitation current, etc. So there's a lot of measurement result, and then this shows I think close to TI memristor, where you have the platinum, and then this is another metal plate in between titanium oxide, hafnium oxide, and then the conduction is formed, meaning that low resistance state when you have oxygen vacancy indicated by white is occupying and making this sort of a connection here, filament formed here. So that's when you have a continuum of oxide vacancy, then you have a conduction, a low resistance. On the other hand, if you apply different biasing voltage, negative voltage, instead of positive voltage is broken, that is a high resistance. So depending on this gap, if it's all the way wide, the highest resistance. If it is close, maybe resistance is somewhat smaller, and so on. And this shows the low resistance LRS state and the high resistance state. And so in this case, it's about, I think, this is 10 to the 4, 10 to the 3. So 1 order. So this is about 1 order of magnitude difference in this particular case, right? Now, going back, if you recall, how was memristor defined? Well, Leon Chua thought there is a missing link between flux linkage phi and charge Q. But yet, as electrical engineers, we are used to handling only voltage and the current. So we write circuit equation in terms of voltage and the current, and then we have differential equation and so on. So there's a book I introduced earlier, Nonlinear Circuit and Systems with Memristors, authored by Fernando Corinto, Moro Forti, and Leon Chua, co-authored, which is using charge and flux as the basic variables. So you have instead of a Kirchhoff current law, Kirchhoff voltage law, you have a Kirchhoff charge law, Kirchhoff flux law. So it defines Kirchhoff law. So you have a Kirchhoff charge law, KQL, right, instead of KCL. The algebraic sum of all incremental charges entering or leaving any coset of this network is 0 at all times for t greater than equal to 0. This is just replacing current by charge. But it says incremental charges, change in charge. You have an incremental flux law instead of KVL. You have KVL, the algebraic sum of all incremental fluxes around any loop of a network is 0 at all times. So instead of voltage, you have now flux. So that's a sort of a definition of a KQL and the KVL. And then you have a constitutive relation, flux, charge domain, and so on. So you model is say two memristor connected. So instead of dealing with the current and the voltage, you deal with the Q and the flux. And this is a model for memristor, for instance. So you have an initial condition, and then memory star without any stored energy, for instance, and then the current. So that's a memory star model like this for corresponding one memory star, another memory star model like this, and then you can apply KQL and the KVL to this circuit for doing circuit analysis, and this shows some equation, initial conditions, etc. So if you're interested, then you can look into this the book, and this shows a capacitor with a memristor. So you have a capacitor model with a initial, the charge, and then memristor model, and you can write down equation for analysis and so on. This is yet another case, and you have a memristor, capacitor, current source, memristor, inductor, and so on. So you can introduce a circuit model for it, and can write the equation for that, and then solve it. So this is one application of that one, memristor-based chaotic circuit. Schwarz oscillator. So Schwarz is the one who invented this circuit. It's called the Schwarz chaotic circuit. And you have a memristor, one capacitor, one resistor, and then another capacitor, and then inductor. You can have a parasitic resistance in inductor. Like this, you can write down equation and so on. And you can show that there is a chaotic attractor of a third order memristor-based oscillator for particular initial condition Q naught. Q naught is equal to 0, yet when Q naught is equal to minus 0.0347, for the same circuit, the chaos generated is quite different. This has like two openings, two eyes, whereas this one only has one eye, for instance. So this is an interesting analysis, but you can do this analysis in circuit VI domain, but this shows that you can do that also in FQ domain, right? So again, this is in chapter 6 of a nonlinear circuit and systems with the memristor. Yeah, and then original, the chaos circuit is by Ito and Chua, memristor oscillator, International Journal of Bifurcation and Chaos, year 2008. So that's a well-known publication in case you are interested in chaos. And this extended memristor diode, so you have a memristor. So if you measure this Lissajous figure, usually it's symmetrical when they are symmetrical. But when you add this nonlinear resistor, which is described by this Shockley diode obeying equation here, exponential V over eta Vt, thermal voltage minus 1. Then you distort this Lissajous figure to create a figure like this, for instance. So you can create a model and then simulate, write code and simulate to get this Lissajous figure, for instance. So this is a pinched IV curve in response to sinusoidal voltage signal Vt is equal to sine 2t, and then this is a current. But because of this nonlinear component, you behave like this. So yeah, when it is a positive, then there's added current, so that's why you have this current peak. In the negative direction, this is almost off, so you get just a normal behavior. Now, memories is standard cellular neural network. Cellular neural network. So you have a cellular structure, but each cell here is composed of a circuit like this. And in it, you embed a memristor across this operational amplifier here. And you build this circuit, you operate, then you can have a nice application. For instance, suppose you have a pattern like this in this rectangular grid. So you have a bar and then singles, the cube area or vertical bar, etc. So if you want to find the horizontal bars, for instance, this is the cellular neural network with the memristor will produce this pattern. See, this is a horizontal bar, and then next row another horizontal bar there, and another horizontal bar, And then here is another horizontal bar. This thing is not counted because only one grid wide, so they are neglected, but it has to be more than 2, then it's detected. So here 2 is detected, this one is not detected, this is 3 is detected, this one is detected, for instance. So it produces that very, very quickly, for instance. So that's one interesting application. And we earlier talked about how they operate, how you can embed this memristor on top of a MOS structure. So you have a MOS transistor here, source drain, and then you have a drain contact, one metal plate, another metal plate, right? And then in between you can build the memristor. So you can build the memristor array on top of a CMOS plane. And this another shows. But earlier we talked about having to add this MOS transistor as a switch to prevent what is called sneak currents. Yeah, this is a headache, sneak current. So safe way is embed this MOS transistor in series with the memristor like this, and then you apply the voltage here. This is called the word line, whether you select this memristor or not. So when you apply word line here, this is turned on, so switch is on, on. So these memristors get involved. If you do not want to select this, you say 0, then this is off. So they are out of a picture, for instance. When you apply this on, this is on in action, for instance. So you can have a memristor in series with a transistor like this. So this is a popularly used. Earlier we talked about 1T, 1R. Yeah, this is precisely that array, right? Now, back in 2011, my colleague Sang-Ho Shin and our group published a paper, Memristor Applications for Programmable Analog ICs. So you can program analog integrated circuits, which we published in Nanotechnology Transactions in 2011. So you can have a reconfigurable electronics in that regard. Utilization of a non-volatile adjustable resistance, a programmable analog circuit, for instance. So this is the programmable voltage amplifier. You embed the memristor here. So you replace a resistor with a memristor here. And you program this memristance using this sort of a pulse. And then, see, you can change this memristance by applying positive swing or negative swing. So you can control this memristance resistance, starting from initial value to decrease all the way down here, or you can increase again back by applying this pulse signal there. That is also handy when you have a neuromorphic circuit. You have an input coming from a neuron, and then you have a memristor here. You can program this memristance, or rather conductance or memristance individually, and then you have a different weight. Then you apply this voltage with a different weight. Your current is summed up here, and then induce voltage, and then that is outputted. So this is a concept. Input coming from neurons, different weight determined by this memductance, and then you have a threshold logic, and then you output and so on. So that is a good application of a memristor. You can program memristance or conductance by doing that way. And that is used in neuromorphic computation a lot, actually. Also, you can have once you do that, you can have a tunable active memristor-based bandpass filter. So for one value of a memristance here, you can program, as we saw before, you can have this type of a bandpass filter with a rather low frequency, but you can change the memristance by doing programming. You change it to 10 kilo ohm. So this one was this one was a 10 kilo ohm K red one. And this one is a 3 kilo ohm. Yeah, you program the memory distance, then it becomes a band pass filter at a higher frequency. So it's very handy. It's a fixed structure. You don't have to go in and change this resistance. You can program this resistance. So that's a nice application of a memristor, right? And you can do also AB amplifier by using same principle here, memristor change. Now, there is another application here. This is a memristor-based analog circuits. The problem with the memristor-based analog circuit, which is sensitive, is that memristor itself is not strictly constant. There is a variation due to process variation or temperature, environmental ambient temperature type of a thing. So they face reliability issues due to their susceptibility to variations in the environmental conditions and the manufacturing processes. So although you design, but when you manufacture, the characteristic may be all different. So how do you overcome that? So this is one solution. You have a proposed the memristor D to A converter DAC. You have another D to A, and then you have a clocked the switch here, and then you have a successive approximation register here to produce output. This produce much more stable successive approximation register, analog to digital DAC using memristor, produce a very, very reliable. So it overcomes the variation in memristor characteristics. So this is one system solution, how you can overcome this one. It's just like a feedback control to some extent, right? So yeah, given his noisy environment, by using this circuit, you can overcome and compensate. So that's nice novel applications. The other thing is, again, back to Chua circuit, chaotic circuit using bipolar memristor. So memristor is a bipolar because it has one branch and then another branch. So one branch and another branch. So this is a high resistance. This is a low resistance stage. So you can switch it back and forth. But you can see that the slope is always positive in this case. In order to create a chaotic behavior, you need some locally active device. So what you can do is you can embed negative conductance in parallel with the memristor here to create curve like this. So instead of going positive like here, you can introduce a negative conductance here. Combined together, it produces this curve, yellow one, red one like this. So it has a combined effect is locally active. Slope is negative. So that becomes a locally active circuit. And that can be very handy, actually. So earlier we talked about, how come in the Hodgkin-Huxley model, you have a potassium channel and sodium channel. And, I think it was the sodium channel has a M and the H variable, whereas the potassium channel had only N to the power 4, the other is M cubed times H. And that was to show it's a negative slope, locally active negative slope. So, when you have a locally active device, like here, it's a combination, it can be very interesting, create this oscillator type of a thing. So this is Chua circuit with a bipolar memristor. And then how do you make it happen? How do you tune this type of a thing? This shows the algorithm, how you do that. And this is a circuit implementation of that one. So you have a memristor here, and then you program this memristor with a negative thing, GN. So this shows how you find the GN and all that sort of a thing to create this type of circuit behavior. Yeah. So as you tune differently, then this dynamics will change also. So that can create a very interesting movie. So here again, Schwarz circuit, known as a Schwarz, known as a Schwarz circuit, is a simple electronic circuit that exhibits classic chaotic behavior. This means roughly that it is a non-periodic oscillator. It produces an oscillation waveform that, unlike an ordinary electronic oscillator, never repeats. That's why it's chaotic. Never repeats. It was invented in 1983 by Leon Chua. So Leon is a very creative person. Now the other application, random number generator, true random number generator circuit using memristor noise signals as an entropy source. So it was published by J. Park. You can look into this here. So as you can see, this is a memristor, like a TI, the HP memristor, top plate, bottom plate, and tantalum oxide and aluminum oxide here, a composite of two. And when there's a bridge is formed, column is formed, there's a low resistance, LRS state. When it's broken, it's a high resistance state. Yet this formation, tend to be noisy. It wouldn't be always the same. That's why it can be what is called a telegraph noise, a random telegraph noise. So when you have an input voltage here in series with the memristor, the output voltage here, the voltage you produce here, it tends to be noisy and unpredictable noise. That's how at the end they create really random number generation. So true random number generation, because truly this memristor is creating telegraph noise truly random. And that's a circuit, so random number generator circuit, but it's inputted through this memristor here. And then bias independent circuit, exclusive O and the NP counter, etc., are going into the flip-flop and then produce output. So this shows how it happens. So B here is node number 1 here, output voltage here is like this. Negative voltage, about around -3 volt. And after going through this circuit at node number 2 here, is shifted up, producing this rectangular pulse like this, right? That's node number 2. And then node number 3 is here. After exclusive OR gate is shown in blue here, like this. And then output node number 5 is shown here, like here. And so here, if you trace it, it becomes 0, move to high 1, 1, 1, 0, 0, 0, 0, 1, 0. So this is a sort of a random number generation based on the state of this memristor here. And the next one shows more in detail. It's a cleaner copy. So you have node 1, node 2, node 3, node 4. So this shows all different and the random number generation output. So memristor can be used for truly random number generation function. And then the other one, same principle, physically unclonable function circuit for hardware security. See, hardware security becomes very important. So you can use a memristor to create a unique signature, physically unclonable function circuit. So this shows that circuit. So memristor intensify the uniqueness and reliability of physical unclonable functions. So that's another interesting application. So it's a very active. So this shows performance metric. The memory is the theme of performance, uniqueness, uniformity, reliability in terms of temperature, and reliability in terms of voltage. So it's 99%, 99%, so pretty high. And then variability aware memory restive crossbars with image split neural architecture. This is the Professor Alex James, some of you may know. He published on nanotechnology in year 2024. So a lot of people question, if you use a crossbar array with memristors are not reliable. The variation in the processing or environmental condition. So how do you overcome that? In this paper, they propose how you do that. So one application is variability aware. So you know that they are variable. So how do you overcome that variable? So what is proposed in this circuit is, suppose you have an image. So instead of handling whole image as a one shot, you split the image into 4 pieces, and then you individually process that split image and then combine together. And then you get better. So splitting the input and independently training smaller neural networks performs better. That's the message. So they demonstrate that, if you do that, it tends to perform better. So instead of having whole image and then feeding it to crossbar array, you divide it into 4 pieces or 8 pieces, and then divide this smaller piece, feed a smaller piece to smaller crossbar array, maybe 4 times a different one, and then compose output together. Then you get a much better performance. So that's the interesting observation. The other one is a bridge memory super resolution crossbar. So you have a neural network, neurons, synapses, is another layer, and so on. So now you have a crossbar, right? Each crossbar has some memduct and some memristor in it, and that network may be consisting of a structure like this. But instead of using single memristor, there's some overhead. You use 5 memristors in this structure. And so a single memristor in the crossbar node is replaced by 5 memristors connected in bridge configuration. That's an innovative solution. The bridge node is programmed by using 2 transistor switches, so 2T5M. Bridge is super resolution node. It has a high number of conductance levels, and thus resolution becomes much better, for instance. So that's another interesting application. So given noisy environment, how do you overcome it? So you, instead of using single memristor, you use 5 memristors, and then that tends to have a better control. So that's there's overhead, but it provides higher quality. So this is by Alex James. They published in year 2022 in Journal of Emerging and Selective Topics in Circuit and Systems. So if you're interested in more detail, you can read that paper. So that's interesting application. Real-time tumor detection, biology, the medical application using electromagnetic signal with the memristive echo state networks. So you have this memristor crossbar array here in this system, right? So this is a memristor array applied for real-time tumor detection. And the memristor crossbar array using a voltage threshold adaptive logic, adaptive memristor VTIM model for the prediction of cancer. So it produced accuracy of about 78% after incorporating compensation for signal integrity, influence, and so on. So you need a compensation, but still produces some good result. Now, getting into logic, digital logic, right? So when HP people produced the memristor in the beginning, they also introduced what is called stateful implication logic. It's rather complex. It requires multiple stages to make it work. So I wouldn't go into detail, but in principle, you can do logic operation if you have the stateful implication logic operation. So it shows some operations and then output and so on. So that's one type of logic using memristors. And then the other one, more popularly, is magic. Memristor aided logic. Shaha at Technion in Israel, when he was a student member, worked with his advisors, Avinom Klodny, he was a faculty member, and Uri Weiser is another faculty member. So they introduced the concept. So when you have, by the way, the Kavatinsky is now a full professor at the Technion. He's doing very, very well. And now I think he's visiting University of Michigan, Ann Arbor, as a visiting professor. But when you have a memristor, input terminal, output terminal, and when you have a current flowing, depending on the flow of a current, resistance either decreasing, or if you have a reverse current, resistance increasing. So that's how you configure this circuit. For instance, you have two memristors in parallel with this orientation, see, dark one as an input side, but output, you reverse it. So dark one is on the output side. And then if you apply Ohm's law and then, all this analysis, then it produces a no-to function. No-to function. If you have n of them in parallel and the output memristor like this, is a no n input no gate, for instance. And so you can have magic no or and gate in this array, for instance. So they can do that, and then this shows when input is 0, input 1 is equal to 0, input 2 is equal to 0. So here is the input is the resistance state of a memristance. So the both are in this case is input 1 is equal to 0. There's a low resistance. Input 2 is a low resistance. And then in this case, output is equal to also low. It's like O2 function. When you have this configuration, this is not inverse, right? So you have the same orientation like here. And then when the input is high, input is sort of a high, input is low resistance, and then the input 2 is a high resistance. I'm sorry, this is a high resistance, and then this is current now here. So the input is equal to 0 means that current is low. Input 2 is current is high, right? So this one is a high resistance, a low resistance. And then output is low, and so on. So you can have that one. You can have also the serial connection, which works as an AND2 gate. So orientation is important. There's the same orientation, and then you have an AND2. This shows logic behind it. So you can use that one. Now, you can also use this configuration. You have two memristors connected in parallel. And that is corresponding to AND two input AND. If you have a reverse direction of memristors and the two input, this is O2 configuration. So when you have a bipolar memristors, R off, R on, and if you use memristor in this configuration, you can realize AND2 function, O2 function, among others. So you can then also use a universal logic gate. In this case, there's 4 memristors like this, with a particular orientation like that. You see, A, B, this is a stick bar is here as an input, whereas here, stick bar is as output, for instance. And then you have an inverter here, CMOS inverter. And then if you tap it here, it's O. If you tap it here, it's exclusive O. If you tap it here, it's AND. So it's a universal logic gate. You have a O, exclusive O, AND. So you can use this unit, AB, with the terminal AND function, O function, exclusive O. You can build a 4-bit carry look-ahead circuit. So you have a memristor and then universal logic gate, and to create the 4-bit carry look-ahead adder circuit. So what does it do? It has a improvement in packing density. Instead of using a full CMOS, if you mix with this universal logic gate and the memristor, look at this. In the full CMOS case, you need 248 devices. Whereas if you use improved logic gates, you can get by with 80 CMOS, 80 components rather. So yeah, number of memristor is 80 CMOS and then 76 memristor. But memristor doesn't cost any area because you can stack on top of a CMOS. So you are really comparing 80 versus 248. It's a factor of 3 difference in terms of packing density in that regard. So this has a merit in it, right? So this shows high density memristor CMOS ternary logic. Now, this one is also interesting. Instead of bipolar logic, 2-level logic, you have 3-level logic. So if you look at this, low, medium, high, low, medium, high. See, 0 volt, 0.5 volt, 1 volt, right? So you can have one input like here, and another input like this. And then you can have exclusive O, exclusive no type of a function out of this circuit. So you have a TO, TNAND, TAND, and then T invert, and then you create a T exclusive O, ternary exclusive O, ternary exclusive no function. So you can build this sort of a gate, and that shows how you build a TNAND gate and the T no gate, for instance. So this is A is a T NAND gate here, and this is a T no gate here, for instance. And this is the inverter function. So you can, this is also ternary logic. Many people looked into multiple logic family, but using memristor, you can realize the ternary logic rather compactly. And the memristor ternary NAND no gates, so that shows. So silicon consumption of the thing. So if you have a TNAND, this is a digital CMOS versus memristor CMOS here. So it's lots of difference, right? Here, inverter, negative inverter, positive inverter, and so on. And there is some hardware experiment here. Memristor CMOS ternary NAND no gates and the application to active matrix display full adder. So this was published in year 2021 by Professor Xiao Wang. She's a professor in China, and worked with my colleague Kemran Jason Eshragian and myself as a high density memristor CMOS ternary logic family, published in TCAS 1 in 2021. So this is a circuit, and this is a input to input and then output. And this is a hardware demonstration of a thing, and creating 1, 2, 3, 4, etc. The ternary logic gate, TNO folder. So there's other people, practical implementation of the ternary logic using memristors and the MOSFET. It's a similar thing, but I just want to show you as a reference. And this shows a ternary full adder, unbalanced. So 3 logic, 0, 1, 2 case. Balanced one is -1, +1, 0 is a balanced logic, 3 different one. And the ternary inverter, and the truth table, and the memristor MOSFET balanced ternary logic. So it has a 3 state, minus 0.5, 0, plus 0.5. So this is a 3 distinct state, right? 1, 2, 3. But it's a balance between negative and positive voltage, right? Yeah. So this shows T NAND and T NOR gate, the balanced ternary logic. And this shows how you build a full adder circuit. And this shows, yeah, this input, carry in, and then there's a different A input, B input, and the sum, and then carry corresponding output for that. So it's a functional. The ternary memristor. So memristor is usually binary, but combining the binary memristors with adjustment of set reset voltages, you can create a ternary logic with 3 different states. So this shows graphically how you do that. So you have one binary and then another binary with a different set reset voltages. When you combine it, you can create a shape like this. So you have one resistance state, another resistance state, and another third resistance state. So it has a 3 state. So ternary logic is a multi-valued logic with 3 different logic states. The tri-valued memristor is a crude element which exhibits 3 different states, resistances, matching 0, 1, and 2 in the ternary logic without using any additional devices. In this paper, the resistances of a tri-valued memristor are used as the logic state variable, namely RH, R medium, R low, are used to represent logic 0, yeah, 1, and 2, for instance. So this is a ternary memristor, for instance, here. This shows some truth table for O function and the inverter function. And then you can, yeah, O gate and the different logic gate configuration. And then parameter of a ternary memristor model, parameters, value, A, B, and then C, D, E. This is all the parameters used in the memristor model. And the value and the resistance. High is 10 kilo ohm, low is 100 ohm, medium is 1 kilo ohm, for instance. So you have 3 distinct memristor value. You have different threshold values. So set reset the threshold. One is 0.9, the other one is 1.1. So you can create this type of device. And so that's again ternary memristor. And this is dynamics of that ternary memristor. And then this is a truth table. This is the crossbar array of the ternary memristors. And you can use this as the ternary crossbar array. Yeah, ternary crossbar array. So this was a memristor crossbar based on novel ternary memristor model published in Nonlinear Dynamics in November 2023. So if you want to find more detail, you can look into this one. So instead of a binary, you can have a ternary, and then you can program also ternary logic in this configuration. You can also use this one to create unique the logic gates in this array. So that's the truth table operation process. And this shows the simulation result, a truth table and the simulation result for different input combinations. The LT spice simulation results of ternary exclusive NOR gate and ternary exclusive OR gate function. So it shows 0, 2 value, and 1 value, etc. So you can do that. Now, earlier we talked about the memristors developed at technical University of Dresden. So they call Techie Fab their laboratory, Techie Fab. So that's why I called it TIF, T-Tech I Fab, TIF memristor. Real-time data processing and storage within the same memristor cell. So the materials they use is a BFO-based non-linear memristor. So it's a BFO is a chemical symbol. It's like this, BIFEO3. So this is I don't remember all this the chemistry element name, but there's a BFO, BIFEO3. So different material composition based on nonlinear memristor has 2 write branches and 2 read branches with the dynamic and the static internal state variables respectively. So this shows this Lissajous figure, voltage current Lissajous figure. It's quite symmetrical actually. So it can read either this one, that's a low resistance. This one is a high resistance. So you have a 2-state read, right? And you can also have a write branch. So, you know, right branch, and then another right branch. So this is 3 is a right branch, 1 is a right branch. This is a read branch, and then this is a read branch. So it has a 2 read branch, 2 and 4, 2 right branch in this case, 1 and 3, for instance. So that's why they call 2 right branches and 2 read branches. And then they use, instead of a flux and charge, they say current momentum, meaning that integration of current. So it's like a charge. And the voltage momentum is like a flux linkage, integration of a voltage. And they create this hysteresis curve between the charge and the flux. So now they have a symbol phi as a function of Q, for instance. So this is read, and write, and that sort of things. So this TIF memristor chip carrier contains TIF memristor chip with 8 to 16 single memristors in this package here, right? Just like norm memristors. But I think this is more advanced than norm memristors. In a plastic lid closed printed circuit board as carrier, the novel memristor device provides a nonlinear behavior in parameter space, the voltage and current, as well as temporal independence of both variables. The latter provides a stationary and persistent memristor state, which can be utilized to store information. Memristors on the TIF memristor chip carrier typically show current voltage single hysteresis. The TIF memristor chip carrier has a size of 14.1 millimeter by 38.8 millimeter by 3 millimeter maximum height, including lid. So that's a dimension. Demonstrator to compute significant pairwise correlation of input sensor data at the edge and to determine corresponding state of the system in real time. So they use it for weather forecasting and that sort of things. A lot of fast correlation based on sensing. So this correlation computing using hysteric memristance, Techie Fab's chorister. So the Schmidt is a researcher. She has a video on this one. Actually, you can watch the video how they come up with this and the working principle. So current voltage, momentum current, momentum curve memristor with non-crossing IV curves have a hysteric memristance. So the interesting thing is, so this is somewhat different. So in conventional memristor, usually you go here, switch high. When you decrease, it'll come down here, but instead it continues here. See, it's not crossing. So that's why it's called a non-crossing. So that's it's a zero crossing is here. It's still zero, but instead of continuing on this branch, it takes a different branch, comes back up, and then it goes here, not continue. So that's somewhat different, right? So again, goes up, and then comes down, 0 here, continue, 0, comes down, and then turn around, come here, continuing horizontally like here. So that's why it's called non-crossing IV curves have a hysterics memory distance. So that's an interesting case, all kinds of different things. Intel, they have what's called octane memory with a 3D cross point. See, it's a cross point. It's like a crossbar. They don't say what technology they use, but many people guess it is a phase change memory they have. So for many real-world storage applications, using octane DC memory and then non-volatile aware file system will drastically accelerate performance. Additionally, user space applications that are non-volatile memory can achieve even greater performance benefits when software overheads are already low. So this one is promoted by Intel. Intel obtained memory specification 58 gigabyte, for instance, and sequential read per second, 1450 megabyte, sequential write 640 megabyte per second, random read, random write, read latency 6.75 microsecond, write latency 18 microsecond, for instance. So that is commercial. And again, in terms of memory technology, after seeing all this memory register, access time versus density, now SRAM here, right? DRAM is denser, right? More packing density. Memory register is next to DRAM. In terms of speed, is better than DRAM, right? Speed is better than DRAM. Whereas NAND flash is although more compact, higher packing density, but it's much slower, for instance, compared to memory register. So this shows some maybe in a market analysis how big the market is. So yeah, so this is what $52 billion market DRAM. NAND flash, $39 billion market. Memory register is yet $250 million market. It's not mature, not commercially as active as other technology. This one SRAM, $90 billion market. So SRAM is high in that regard. This is a nice chart to show different technologies. So now you distinguish RRAM with a PC memory, phase change memory. This is a memory register still, but you define RRAM like HP type, right? And then phase change memory, and this is a magnetic RAM. So RRAM mechanism observed in 1962. Phase change memory mechanism observed in 1962. So well before memory register formal definition introduced in 1970, right? Here. And then developed. So Samsung is using 1T, 1R, so 1 transistor, 1 resistance, 0.18 micron RRAM 2004. And then 2013, 24 nanometer, 1 switch, 1 R, 2 layer RRAM for 32 gigabit memory. And then Weebit, that's the automobile market company, 130 nanometer RRAM, qualified for automobile industry 2023. And the Tetramem is a startup company, Tetramem, 11-bit per cell RRAM. Yeah, so each cell has 11 bit. The many stable states, but 11-bit is a lot actually. 2024, TSMC, RRAM, SRAM, 22 nanometer IMC chip 2024. And then phase change memory, STMicron in 2025, 18 nanometer automobile MCU with a PCM 2025. IBM 2024, 14 nanometer, 64 core IMC with a PCM 16 megabit. And MRAM, right? Samsung target 5 nanometer MRAM by 2027. So they're still competing. You have RRAM, phase change memory, and MRAM. And the Renesas is a Japanese company, 2022, 22 nanometer MCU with a STT MRAM. Yeah, there's a spin torque transfer MRAM, 11 megabit 2024, right? Yeah, so this is a 11-bit per cell RRAM. Yeah, 2024. So it's sort of about same here. So that's the sort of state of the art. It's published in Nature. Yeah, 2025, April 2020. Yeah, I just captured this recently. So that's a report, state of the art. Comparison of phase change memory, RRAM and MRAM in terms of performance, the same publication here. So it compares, this is a nice chart actually. How about the bit cell area? The smaller the better, right? So if 0.01, 0.05, 0.1, so if it reaches here, it's better. So MRAM, for instance, is here, and phase change memory is here. And I think RRAM should be also, RRAM is about here. So yeah, so maybe it's a RRAM in terms of mask technology is not as aggressive as here, but they're very close. CMOS compatibility, RRAM is best. That's important because you still need the CMOS for a long time, and RRAM is most compatible with CMOS. That's good. In terms of a ratio between high resistance and low resistance, the PCM is 50, and I think this is not quite correct. The RRAM is about 10 here, but it's much more. Actually, there are some numbers even exceeding 100 and so on. So that is not quite reliable here. Speed-wise, in terms of latency, nanosecond, RRAM is best. Yeah, RRAM is here, maybe 40 nanosecond, whereas MRAM is more about it, maybe 40, 50 nanosecond. And PCM is about here also, about 50. So in terms of speed, RRAM is better, right? Energy, picojoule, RRAM is better compared to MRAM. And also phase change memory is the poorest in terms of energy. Endurance, MRAM is so far best. And the retention, years, here is a PCM, seems to be more mature PCM. Voltage, the smaller the better, right? So this one, MRAM still has more than 1.5 volt. And red one is RRAM is less than that. And the PCM is somehow lower, but that cannot be quite true. Actually, PCM requires some high voltage, so I think that is not quite correct. Number of states, RRAM is 64, but more than 64 actually. It's Joshua Young at USC demonstrated more than 1,000 state actually. Yeah, so that's far better than any other technology. Stochastic property is low, So the lower the better, actually. So the MRAM in that case is better in terms of random variation type of thing. So that's a very nice chart. So in order to be perfect, you want to reach every corner. But so far, they are being underdeveloped. Weebit Nano, right? Automotive grade product achievement attest to the quality and reliability of a Weebit RRAM IP for automotive grade product. That means a lot. I said, when you talk to automotive manufacturer, it's very hard to sell electronic components. They're very conservative. They don't want to risk liability. But if you qualify for automotive grade product, that is a very, very good, actually. So this is a news release, March 11, 2025. This company, by the way, is in Israel. Weebit Nano Limited they have a stock market. A leading developer and licensor of advanced memory technology for the global semiconductor has completed AEC-Q 150-degree operation qualification of its resistive random access memory module in semiconductor manufacturer Skywater Technology 130 CMOS process. So that's very, very good. Actually, I was very excited to read this news release last March. So that's very good. There are many, many books written on memristor and memristive systems. So this book we mentioned, nonlinear circuit and systems and memristors, development of a memristor-based circuit, Professor Yu in Australia and Andrew Fitch, they have one book, memristor emulator circuit. So there's one book on that, Springer. Nanoscale memristive devices and circuit design, also is available through Amazon. Memristor and memristive systems by Ronald Tetzlaff. He's heading the Chua Memristor Center in Germany, in particular TU Dresden, Technological University of Dresden. So he edited this book, has been read a lot. And then memristor's Intech Open book, I think it's Alex James did that. Memristor-based nano-electronic computing circuit and architecture by Vukas and Sirakulis. I think they are in England and Greece. And then memristor computing systems by Chua Tetzlaff Slavoda. They edited this volume. Memristive nonlinear electronic circuit dynamic synchronization applications. Another book, Advances in Neuromorphic Memristor Science and Applications. And Advanced Memristor Modeling book. And then another memristor book. And the memristor for neuromorphic circuit and artificial intelligence applications. And then system design with the memristor technologies. And the memristor and memristive neural networks. On the mathematical modeling of a memristor, capacitor, and the inductor book. Advanced in memristors, memristor devices and systems. Another memristor book. Memristor-based logic architectures. Interesting. Looking, it's biologically motivated, right? Memristor networks by Andrew Azamatsky and Leon Chua edited this book. Andrew is in England. Nanoscale memristor device and circuit design is edited by these people. And then design of a read-write circuit for memristor-based memory array. Another interesting book. Memristors and its application in VLSI design. Memristors in brain-like computing. How about that? Chaos, CNN, memristors, and beyond. So it's again Andrew Adamaski and Gunrong Chen. I think he's in Hong Kong. the Chua lectures from memristors and cellular nonlinear networks to the edge of chaos. It's a Chua's lecture book, handbook of memristor networks, low power memory memristor devices and systems. Chua lecture, another volume here. Memristor technology, synthesis and modeling for sensing and security applications. Another book, memristor and the memristive neural networks. I think that's it. So there are many books, many papers written on memristor because it's an exciting topic. As I said in the beginning, Leon Chua introduced a conjecture that this existence of memristors based on a flux charge constitutive relationship. But what was most exciting, really epoch of this all activities, really the HP's fabrication of a memristor. Although it was not ideal memristor, it's a solid state memristor. That matters. You know, without solid state, we wouldn't have AI or many electronic systems. So that is very significant. That is exciting, in fact. And whether you have a 3-terminal memristor system or transistor or 2-terminal memristor, that is very exciting. I think we welcome any kind of a novel device as long as they can be used for good applications. In the beginning, there was lots of criticism about Chua's memristor. People argued that that's not right, but that motivated lots of development, and that led to the development of a fabrication of a memristor at HP in year 2008. So for that, I think they deserve a great, good credit and. Yeah, so it is an exciting field. And, when people argue that the pros and cons of AI technology is any revolution, industrial revolution, there's always a criticism. When you had a mechanical motor, people criticize. Yeah, it takes job away. But we are riding car right now. When electricity was created, people also criticized, all that. But as innovative engineers, we capture this new technologies right on it. We use it, develop new field. So that's what is exciting. So memristor is there. We develop on top of memristor concept to introduce a new technology, new gadget, new systems. That will make things a lot better. Again, to quote Jack Kilby's Nobel Prize speech, Nobel Award speech, it's VLSI is good to lower the cost, simplify assembly, and make things smaller and more reliable. So if we can achieve that, I think we can contribute a lot. So you all should be very excited about this new technology. It can be better technology. Then it's all the better. Nobody should say that the memristor is the ultimate technology. No, I think there is always many people used to say even a few decades ago, all the research has been done, but that's totally not true. And if you say that memristor is the ultimate device, that's not true either. But this can be a good stepping stone, and we should utilize it and then come up with an even better one. And whether ideal memristor is existing or not, that's secondary in my view. That motivated fabrication of a solid state memristor, which is not ideal memristor, but this new device can be utilized, applied for lots of different applications. You saw all different exciting memristor circuit and the systems, right? So be on it and be excited, and hopefully you can create a lot more good things using memristor technology and applications, or improve on it. So that's the end of today's lecture, and I'm open for your questions now.
Thank you very much, sir. So
You're welcome.
definitely you said about that we are in the stepping stone of the advancement. Definitely, sir, your insightful and thought-provoking lecture is curious generating. Definitely we get benefited of it. Any participants you ask, you may ask the questions now. Sir, can you able to see the chat box?
Let's see whether I can see the chat box. Okay. So let's see. Last time I was not able to see the chat box somehow. Let's see. See, I don't have access to control box.
Yeah, mic on.
Let's see. Okay. So now, yeah, there's a chat box, view, react, raise. It's a chat. Okay, here. Okay. Now I see the chat box. Yes. So let me read the chat box here. So my question is, does LRS state construct only one filament or many filaments? It could be many filament. So it depends on device. I wish I could take a picture of inside the operation, but it could be many filament. It doesn't have to be single filament. It depends on device operation. So then if it's the many filament, how should we validate which one is the best? Well, they're all in parallel. So like you have a resistance in parallel. The more you have, the lower the resistance would be. So it's not just a matter of which filament you choose. So if either you have a very thick filament or many of smaller filaments, so whichever contributes to low resistance, that's what we want. So we have a high resistance and the low resistance. I hope that answers your question. And then, good morning, sir. To design a digital circuit using both memristor and CMOS logic using Cadence virtuoso tool using Verilog A model, is there any standard code or textbook or any source of memristor Verilog A model? Please suggest, sir. I think you should read the memristor model book. So I listed the books, and you should look into it. There are also many papers written on it. So if you do Google search, I'm sure you will find it. Yeah. In slide number 66, could you please explain how 0, 1 result in zero logic state? Let me see. 66, right? 66. 66. Yeah. Let me see. 66. 66. Slide number 66. That goes back. Is it today's 66 or the original 66? No, that's so I think you are referring to today's 66. So if I start, that should be 66, 194 maybe. No, 66. 66. So let me see. You just stop me. 128.
Sir, it's 166, not 66.
166. Oh, 166. I'm sorry. Okay,
Yeah.
that's good. Okay. Here. So 166 here. Right, 166. So question is, let me see. Could you please explain how 0, 1 results in zero logic state? So 0, 1, 0, 1. So this is a 0, 1, right? So 0, 1 is this itself is ordering, but this is inverting. So this is ordering is 1, but the inverting is making it 0. So that's how you get output 0. So red one is output here, right? So when it is yeah, when it's a zero current, right? This is low current, this is high current, and then this one is inverting. The high current is flowing and then ending up producing a low output. So yeah, this is the, wait a minute, this is a O-ring function. Okay, so you maybe, yeah, so this is a O2, so this is 0, 1. O-ring should be high. So this one is output is high. Yeah, sorry, this is output is high. And the initially is 0, but output is high. So sorry. So 0, 1 high. So this is output is high. So this is O2. And here is a 1. This is a 0. So high, low. Initially low, but output is high. And the high produce a high. So this green is output. I'm sorry. Yeah. So yeah, O2 is creating. I think that answers. So O1 results in 0 logic state. O1. So yeah, this is initially was 0. Its output initially is 0, but output is really green. So output is producing 1. So it's not 1 logic state. It's yeah, 0 logic. It's 1 logic state. So hopefully that answers. Is it possible we can use memristor to design digital circuit? Yes. So you saw that you can use a memristor to design circuit. So TRUAS circuit is made of a memristor or TRUAS diode. Yeah, so you can replace TRUAS diode with a memristor. So originally it was a diode, but you can use a memristor to create. That's what all the papers indicate. Any other question? So which is preferable or ideal for phase lock loop, cross one or touching? I think it has different applications. So if it is logic, I think crossing is better. But if it's non-touching, as you saw, they have different applications. So I think both are okay. Depending on applications. So I give credit to Dresden people also creating good commercial product. They seem to be very proud of what they have done. So that's an innovation. Any other question? No more question? All right, then I will let you go.
Okay, sir. Thank you very much, sir.
Thank you. Have a nice day, and then we'll see you tomorrow again in the morning.
Right, sir.
Right.
Thank you,
okay.
sir.
Good,
Good
have a
night,
nice
sir.
day.
Good night, sir.
Thank
Good night,
you.
sir.
Bye-bye. Bye.
मेरा सवाल था, गलत नहीं था सवाल, फंसा है वो। स्टॉप कर दें।